Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 25th, 2025, about 4 days ago. It introduces Root, a new optimizer that makes training large neural networks much more stable by using dimension-aware orthogonalization and a smart outlier suppression step, which together give faster convergence and better final performance than both muon and atom-based methods. The paper is titled Root, Robust Orthogonalized Optimizer for Neural Network Training. And as we will see later, the implications for large-scale model training are quite significant. Also, the authors shared their work in the broader NOAA research repo from Huawei's NOAA's Arc Lab. Inside it, you'll find a Root subfolder alongside many other projects with Python code, scripts, and notebooks to run the optimizer, reproduce training setups, and tweak configurations for your own neural network experiments. Alright, the previous segment described what Root tries to achieve. Table 1 now quantifies why the older Newton-Schultz setup is fragile. The top block uses one fixed set of coefficients, and the mean squared error jumps a lot as the matrix shape changes, with square matrices staying particularly bad. The bottom block tunes coefficients per shape, which sharply lowers those errors and makes orthogonalization much more consistent across layers. So, while Table 1 focused on dimensional fragility, Figure 1 explains why robustness to outliers is equally crucial. The left histogram compares gradient values to an ideal Gaussian bell curve, and the much heavier tails show that extreme gradients occur far more often than a normal distribution would predict. The right quantile plot reinforces this, since strong bends away from the diagonal reveal many large outliers that can destabilize Newton-Schultz orthogonalization. Well, Figure 2 translates those robustness ideas into actual training dynamics. The 4 panels track relative error for different projection layers, and across all of them, the green Root curve stays clearly below both the blue classic Newton-Schultz and the orange muon curves. That consistent gap means Root's shape-specific coefficients approximate the ideal singular value decomposition much more closely, even with only 5 orthogonalization iterations per step. Alright, Figure 3 connects that improved orthogonalization to real training progress. The plot tracks training loss over 10 billion tokens, with the muon curve on top and both Root variants consistently below it. The orange curve, which uses only soft threshold outlier suppression, already converges faster than muon because it stabilizes noisy gradients. The red curve, which adds dimension adaptive orthogonalization, goes lower still, reaching the best final loss around 2.54. So, while Figure 3 highlighted faster convergence, Table 2 reports how that translates into zero-shot accuracy on common language benchmarks. Root attains the best average score, about 60, slightly ahead of muon and clearly above Atom W. Root leads on tasks like HeliSwag, OBQA, SciQ-Wino, and WSC, while muon keeps a narrow edge on ArcEasy. This pattern shows that the added robustness yields consistently better generalization, not just smoother training curves. Okay, Table 3 shifts from language to vision and tests Root on a small vision transformer trained on CIFAR-10. The table reports top 1 accuracy for muon and for Root, with different quantile thresholds in the soft threshold step. Muon reaches about 85%, while Root steadily improves as the quantile drops. The best result comes at a quantile of 0.85, hitting about 88% accuracy, which suggests stronger outlier clipping helps image models too. Root shows that making optimizers both dimension-aware and explicitly robust to gradient outliers can give faster convergence and better generalization for language and vision models, without changing architectures. The broader implication is that smarter math inside the optimizer can unlock more reliable, large-scale training. That is it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.